Hey, I think we're recording again. Oh, we are. Excellent. So listen, the critics of the last video have said you guys make too much noise. All right. Yep. Mostly famous actresses were really upset with the gentleman. Like really attractive females were like, they sound ridiculous. Okay. Yeah. They said one of you sounds like you drive a Geo Metro way too fast, and you got like a really ridiculous. I think it was you, Natick. They said you drive too fast, like a lunatic. I don't know how they knew that from the video. But look, yesterday we were talking about the disc and washer method, right? I'm pretty sure I just called it the disc method yesterday, but all right. And we're talking about volumes, and we said we find volumes two different ways. We haven't got to both of those ways yet. Okay? Huh? Oh my God, Liam. Boo. All right. So, well done. The idea here is, gang, you're going to see a question that asks you to revolve a region in the plane, like an area between curves. You're going to revolve it around a line. It's going to create a 3D shape. Okay? Let's just start with, yesterday I tried to do root x and x squared. Do you guys remember that?
Yes, I do.
Okay. Let's just look at, just so we can review here. Let's take a look. You know what? Let's not even do root x because it really doesn't matter. Let's do ln of x, your favorite function ever. Okay? Here's y equals ln of x. Cool. And it's going to say something like, oh, y equals ln of x. Between the x values of x equals, I don't know, we'll say e and x equals e squared. Okay? They could be regular numbers. They could be e. It doesn't matter. You're going to have a calculator, okay? And they're going to say, take that area and rotate it around the x-axis is what we're going to start with. Okay? And yesterday we said that's going to create a shape. You can imagine, like, this what this region looks like, sort of, right? It's going to create a shape that looks something like that, to the best of my drawing ability. Okay, that looks awful, but you with me here, okay? I don't like that. Let's draw it here. Something like that.
There you go.
That's a little better. Okay? And we said that can really be considered to be made up of a bunch of circular cards, and we're going to find the volume of each card. We said each card is really a cylinder, and the volume of a cylinder is pi times the radius squared times the height. But because we're making each of these cylinders super duper infinitely thin, what did we say the height of these cylinders was? Just dx. Thank you, Connor. Dx. So the height's becoming dx. The radius is the distance that you're rotating from the axis, in this case the x-axis. So in this case, that's just going to be the y value of the function. Okay with that? That's the radius there. That's just the y value from the x-axis to the curve is the y value. Okay, but you don't put in y there. The fact that we're doing dx means we have to have it in terms of x, but we know that y equals ln of x. So r squared becomes ln of x squared. And you put a pi, and we're integrating from e to e squared. And that's going to find the volume of that shape. Now, sometimes you're asked just to write the integral that finds the volume. Sometimes you're asked to actually find the volume. Sometimes you have a calculator. Sometimes you have to do it by hand. This is one that you would have to have a calculator to integrate this. We don't know how to integrate ln squared. Okay? That's called the disk method because there's only one function and there's no hole in the center of it. So every single cross section, like the small cards, are all just super thin disks like this. Cool. Where the radius was f of x, we said, and the width was dx. Okay? So we're adding up those cards. Okay, and I showed you a couple little computer things yesterday. It kind of made a little sense. Maybe I'll pull up a couple more today. Anyway, if we want to rotate around a different line, so let's say I want to rotate the region that y equals sine x makes. With me here. But you know what? Let's not even do this yet. I take it back. Let's go back to my other question, which was, remember we just said, what was it, root x and x squared? Definitely it was. We're trying to rotate this around. Right there. We know that goes to 1. And we said this is going to be a rotation just like before, but there's going to be a hole in the center. So we're going to find the big volume, and we're going to subtract off the little volume, basically, is what's going to happen. Okay? So Big R is always the one that's furthest from your axis of rotation. Again, all we're going to do is rotate this around. But now our cards, if you can imagine this, our cards aren't going to be discs. Okay? The outer part is going to be a disc, but there's also going to be this hole in the center, like that. Is it okay? That's what's going to happen because we're rotating. Let's think about this disc that will be right here. Rotating that one around like that, but then the little one's going to get rotated around too. It's going to create that hole in every single one of these things. Okay? So all we're going to do is find the volume of the big card and subtract off the volume of the little card. That's the hole in the middle. Okay? And it turns out that the volume equation is the same for both of them. It's just the function you're using changes. Okay? So if you just look at that card there, this is our axis we're rotating around. What's the inner radius? What function are we hitting there? That's x squared. Not dx, that's x squared. Remember, this bottom curve was x squared and the top curve is root x. Okay? And big R, if we go all the way out to the outside of the shape, is going to be x squared. Root x, I'm sorry. Root x, yes. Okay? So to find the volume of the big curve, we're going to do exactly what I did up there with the ln function. It's just pi times the integral of root x squared times dx. Okay? But then we need to subtract off. So pi times the integral of root x squared dx. That finds the volume of the whole solid. But then we got to subtract off the hole in the center. Because the formula is pi r squared h. Where r is the radius, right? In this case, it's the function height. Okay? The function, like the distance the function is from the x-axis. Okay? Now, we're going to move the axis around a little bit, so it's not always going to be just f of x. Okay? But for right now, it is. And then we're subtracting off the little volume, which is going to be pi times x squared dx. And that's going to find the volume of the shape that's left with the hole in the center of it. Okay? And that's called washer method. It's really just disc method twice, but they call it washer method because, you know, like bolts and nuts and washers, has like that's what a washer looks like, not like a clothes washer or a dishwasher. What's up? No. Washer like the metal washer you use to like bolt something. Huh? It's not a lot. Okay. Anyway. Guys, you usually see this like this, and I want you to put this down here. Look. Since we're integrating on the same interval for both of them, they usually just put them together like that in one integral. Okay? And I'm fairly sure we wrote this yesterday. It's just pi times the integral from 0 to, well, let's say a to b in this case. Let's just have like a general formula. From a to b of big R squared minus the little radius squared dx. Okay? And that will find the volume of something rotated around a horizontal line. Okay? So the only real question here is when you're asked to find a volume is what's big R and what's little r. Okay? All right. So let's rotate a crazy one real quick. Let's say we want to take, you know, to keep it simple, let's do the same exact shape for right now, and then we'll practice a couple, okay? So we still have root x and x squared here. But we're going to rotate it around a couple different lines. So up to this point, we've been rotating around the x-axis, okay? Sometimes we're going to say rotate the region between those curves between the line like y equals -3. Okay? Is that going to be a bigger volume or a smaller volume than if we rotated around the x-axis?
Oh, like -3 would be the midpoint?
Yes. It's going to be a bigger volume, right? Because we're rotating it further around. It's going to make a much bigger circle. Okay? But it doesn't matter. It's just some stupid 3D shape. That's all we're doing. But it's going to be a much bigger circle. But the formula for volume is still going to be, there's still going to be, since we're rotating it, these discs with holes in the center. So it's going to be the big volume minus the little volume. Okay? So all that really matters is, when you're asked a question for a rotation is, what's big R and what's little r? And the way I want you to find them always, you ready? You're going to draw the graphs out, just like I did here. You're going to take your pencil. Here's my pencil. You're going to put it on the axis you're rotating around. That's y equals -3 here. Cool? And you're going to draw perpendicular, so in this case that's going to be vertical, all the way to the outside of your shape. Is that going to be the big radius or the little radius? That's the big radius. And all that is a distance. Now, it doesn't matter where I start on this axis. If I draw to the outside, y'all can see, what function am I always hitting? Root x, right? Root x. So the length of that radius, although it is changing, it's always defined on top by root x. It's always defined on the bottom by -3. Sound good? So the radius is just the distance between those things. And the way we find distance is we subtract. Okay? And we always subtract the bigger number minus the smaller number. So it's not, no, -3 is not an asymptote. It's just some line that we're rotating around. Guys, I arbitrarily picked that. It could have been y equals -10, -100. It doesn't matter. It's just some line we're rotating around. But the radius is always going to be the top minus the bottom. What's the top of the big radius? Root x, right? It's a function. What's the bottom of the big radius? -3. So big R is root x minus -3, which we're going to write +3, but does it make sense? And essentially, this hopefully makes sense because all we did was instead of rotating around the x-axis, I moved what we're rotating around down 3. So all I really did was added 3 to the radii, and that's exactly what that looks like. I took root x and I'm adding 3 to it. Okay? But as long as you, again, pencil on the axis, draw to the outside of your shape, that's big R, just do top minus bottom. Okay? Little r is the same thing, except you're going to draw to the inside of your shape. So if you put your pencil on the axis and draw to the inside, that's little r. So that's going to be x squared minus -3, which is +3. And don't shut my vents. Hey, just you accept the heat, man. Okay? All right. All we're going to do for volume is pi times the integral from start to stop, big R squared minus little r squared dx. Okay? So, in this case, that's going to be pi times the integral from 0 to 1 of big R squared, which is root x plus 3, notice the parentheses, minus little r squared, which is x squared plus 3 squared dx. Can we handle that? They didn't say 0 to 1, but root x and x squared intersect at 0 and 1. So that's the area we're talking about. Okay? Is everyone okay with that?
Yeah.
We could do this integral by hand, but we'd have to expand this all out, which would be a pain in the butt. We could also do it with a calculator. Okay? And again, so at this point, since I'm hoping we can all do integrals, we just want to set some up. Okay? So, we're going to take a look at an AP question. Are you ready? Don't everybody get too excited right now. Yes, sir.
You did +3 because of the rotating about y equals -3.
Yeah. Okay. Let's do, this is 2010 number 4. This is a great question. Please don't pop popcorn. Doesn't even make any sense. Do I want popcorn? No. Why do people give me popcorn? Oh, that's okay. That makes sense. No, I don't want it. Yes, Josh, I would prefer if you didn't pick up things that were in my room that don't belong to you.
Hey, YouTube.
All right. So look, here's our question. We're going to pause this video for a second. Okay. Whoa there, Chief. What's up? No, it's not from 0. You got to do the x values. So let's just talk about A real quick here. I know you're all excited, but yo, check it out. If you're asked to find the area, all you need to know is what's the top and what's the bottom, and you got to trace the whole thing and make sure the top doesn't change. If the top changes functions, you need another integral. What's the top of this shape the whole time?
6.
Just 6. And the bottom is?
2x squared.
2 root x. So the integral is going to be just top minus bottom, 6 minus 2 root x. Okay? There's no pi. There's nothing like that. Okay, we're not doing volume. Don't confuse that with volume. It's just 6 minus 2 root x dx. And we have to integrate it. The limits on your integral are where do you want your rectangles to start and where do you want them to stop. We want our rectangles to start over here, which is at 0, and they're going to end out here, which is at 9. So we're going to integrate 0 to 9. And then doing this by hand, the integral is 6x minus, remember, root x is just x to the 1/2. So that becomes x to the 3/2. You got to multiply by 2/3. So that becomes 4/3.
Where did 6 come from? 6 is the y.
Yeah, it's the top. That's a top function.
Is it 18? Would you do 5? 3 halves instead of multiplying 3 halves?
Yeah, you multiply by 2/3.
You multiply. Oh, okay. Yeah.
Cool. And then you gotta do this by hand here. I'm hoping you guys are okay with a little bit of arithmetic. We're gonna plug in 9. That's 54. Very good. And we plug 9. What's 9 to the 3/2?
It's like 27.
It's 27. It says take the square root and then cube it. Square root of 9 is 3. Cubed is 27. Okay, that's plugging in the 9.
It's 36.
Minus plug in 0. Okay, and you just get 0. So 54. Oh my goodness. 27 times 4/3 is 36. Thanks for ruining the surprise, Josh. And when you subtract them, you get?
18.
And what's that number represent? The error of that thing right there. Okay. We're going to do the volume. All right, young adults. Look, if I were you, I would draw I'd draw the whole shape again. Okay? 2 root x looks like this. And then you've got, this isn't the best drawing, but you've got y equals 6 coming across. Let me do this again. That was pretty bad. Yeah, something like that, just so we get that. And then we got this happening there. Great. Okay? That's what we're rotating around. And the line y equals 7 is going to be up here. Okay? That's the axis we're trying to... It doesn't matter where it is. They're going to tell you where. It could be above it, it could be below it. It doesn't matter. All we need to find when we're doing a rotation like this is what's big R and what's little r every single time. You find big R by putting your pencil on the axis and drawing to the outside of your shape. No matter where I pick on this axis and do that, what function do I always hit? 2 root x. That means there's only one big R. If it changed, if for some reason there was like another function I was hitting somewhere else, then I would need another integral. Okay? That doesn't happen all the time, but every once in a while you see that. Okay? So big R is just the top minus the bottom of that. What's the top of those radii? 7, and the bottom is 2 root x. That's big R. It doesn't matter that the 7's on top. Top minus bottom. Little r, put your pencil on the axis, draw to the first time it hits it. What's the top of those lines?
7 minus 6.
A 7 minus 6, which you can just write as 1, but that's what little r is going to be.
Is it really 1?
That's it, man. Okay? So then our formula is pi times the integral of big R, which is 7 minus 2 root x squared minus little r. And all we got to do is say, where do we want my radii to go from left to right? They're going to start at x equals 0, and they're going to go to x equals 9. Okay? And if they want, again, they don't want us to do this by hand, so that's our answer. All right? And usually part C is sometimes like a weird question. Let's check this out. Oh, we can't do C yet because we haven't talked about bases of solids. Okay. How are we doing? Huh? I can't hear you. No questions. We can do this.
Yes, 100%. You can take the test right now.
Okay. Let's talk about disc and washer method. So this is still the same method. But up to this point, we've only rotated around horizontal lines. Okay? We're going to rotate around a vertical line here. It's going to change your life. I'm going to do the same exact shape we just looked at. Okay? Yeah. That was 2 root x. Looks like this. And y equals 6. Okay? And y equals 6. Yeah, we're going to rotate around a vertical line. So listen. Same area. This is a y here. But we're going to rotate around a vertical line. What's a vertical line equation look like? X equals, or they could say the y-axis. They could say rotate around the y-axis, that's a vertical line, or they could say rotate around x equals some number, also a vertical line. Okay, so let's say they want us to rotate this thing around the line x equals -4. Okay, now let's think about this. Now our discs are not going to be vertical discs. They're going to be rotated around like this. They're going to be horizontal discs. Is that okay? That's how we're rotating it. Which means we're not crushing down x anymore. We're crushing down y. Y'all with me on this? Like we're going to have discs that look like this that are super duper duper thin. Okay? Which means what's the height of those cylinders? dy now, not dx. Okay? It's still the same formula. It's going to be big R squared minus little r squared times pi, but now there's a dy in there, which means big R and little r had to be defined by what variable?
X.
No. Well, y, there has to be y's in there. Yes? If dy is going to be at the end of our integral, we have to have y's in our integral. You can't just change the x's to y's, okay? So, let's think about this. We're still going to do the same thing that we did last time. We're going to take our pencil. We're going to put it on the axis. There it is. Oh, there it is. We're going to draw to the outside of the shape. But now we're not going up and down. We're going left and right. Okay with that? Do you see that no matter where I pick on the axis, I'm always hitting the same thing? What curve is that? 2 root x. True? And then so big R has to be involved with that curve. Okay? Little r is going to be always hitting here, which is what? The y-axis. Okay with this? Okay. Now, keep in mind, because we're doing dy, I don't want to do, so this is a very common mistake. Kids will say, oh, big R has to be 2 root x minus -4, right? So remember we said when we're going horizontal, we do right minus left, okay? But you can't say that it's 2 root x minus -4 because we're going to have a dy in there, okay? So we have to solve this for y, for x. We have to solve that for x. We have to get x by itself, which means what's the first thing we're going to do? Divide by 2, and then what are we going to do to both sides? Square it. So that curve is the same thing as this curve. Y squared over 4, or 1/4 y squared. So when you're going around a vertical line, you've got to have your equations in terms of y. You've got to have x equals something with y's in it. So you're basically solving for x as opposed to solving for y. We okay with this? This is true of all vertical rotations if we're doing disc and washer method, which is all we're going to do. Okay? So, if we're going around a vertical line, our radii have to have y's in them, which means if you have a curve, y equals something, you have to solve that for x. Yeah. Because, look, we're really subtracting right minus left, which are x values. I'm really subtracting this x value minus the other x value at the other end. But the x value is changing depending on what y value we're at. So I need a function for the x value is what's happening, an equation for the x value. But either way, what is big R going to be here?
1/4 y squared
Minus -4, which is +4. Is that okay?
What would we do for 6?
And little r is going to be, what do you mean 6?
Y equals 6.
We're not hitting y equals 6. Our little radius isn't hitting y equals 6, it's hitting this right here.
Oh.
What line is that?
That's the X.
It's the y-axis, but what's the equation of it? We need to know what. That's x equals 0. Yeah? So little r is 0 minus -4. Okay? That's the right side minus the left side, which is just 4. And then all we're going to do is drop these into that formula, which is pi times the integral. Big R squared is 1/4 y squared plus 4 squared minus little r squared, that's just 4 squared, and its dy is the thickness of them all. Okay? Now, we got to talk about our limits here. When we were doing x was running from 0 to 9, right? Because this point out here was 9, 6. But now we're integrating with respect to y. So we got to say what y is going to do. Where's y going from? What's the lowest y value? 0, and it's going all the way up to 6. Okay, so that y equals 6. Like when we do it with x, we had to do that was in our radii, but here it's just one of our limits. We're integrating from 0 to 6. Easy enough? Do me a favor. Same exact region. Find me the equation when it's rotated around x equals 20. Very good. Okay. So, again, if you're ever having trouble, just draw the shape again. There's 2 root x. There's 6. X equals 20 is out here. Big R is going to be pencil on the axis every single time. Draw to the outside of your shape. If I do that in multiple places, am I always hitting the same thing?
Yeah.
Yes. What's big R?
The x-axis. Y-axis.
20.
No, 20 minus 0, right? Okay. So let me see what Josh just said. Is I hear that a lot. The big R is the y-axis, right? Big R is not the y-axis. Part of big R has to do with the y-axis, but big R is not the y-axis, okay? What's little r going to be? 20 minus 1/4 y squared. Okay? So all that changes is the radii. So this is going to be pi times the integral. It's still 0 to 6, and it's big R squared, which is just 20, minus little r squared, which is 20 minus 1/4 y squared, and square that, dy. We good? Now look, let's actually find an answer here. So let me show you how to do this in the calculator semi-easily here, okay? So you could type this all into math 9. So let me go ahead, bam. You're going to hit pi, math 9. That's going to give you the function integration thing. If you got a newer calculator, you got like the little integral symbol here, okay? That's fine. But look what I did. Check out my sneakiness. I went into y equals, and I just put big R as y1 and little r as y2. Okay? No, you don't. You don't have to put that there. I just put it there to emphasize that that's what you're doing, right minus left. That's all. Okay? So it's just 20. Yeah, for fun. Yeah, it's just 20. I didn't mean to confuse anybody with that. It's just 20. Okay, there you go. It's gone. Also, look, check this out. If you're doing an integral in a calculator, it doesn't matter what variable is in your integral. When you put it into the calculator, it's going to be an x. That doesn't change what's happening. Like the math doesn't change. Okay, the calculator doesn't know what variable you're using.
Should you put like a parenthesis around 1/4? Because then 20 minus 1 over x squared.
It's 20 minus a fourth x squared. Yeah, you need parentheses around that because it's all multiplication. Anyway, so look, the whole point of this is it saves you from having to put parentheses around your big R's when you type it out. Because look, now that I've got this, I can just do fn int. I can say go ahead and do y1 squared. That's big R squared.
There's an easier way to do that.
Minus, what is it, Liam?
Alpha, then trace.
Alpha trace?
Yeah.
What does that do?
It brings up like a context menu like this, where you get y1 to y2.
Alpha trace.
Oh, I think the trace is 3.
No, this just did this.
I think yours has a previous PI on
Okay.
the other calculator.
All right, well, I'm not that fancy. But alpha trace, if you have a newer calculator, Liam is saying does some fancy stuff. We're going to do comma x, and we're integrating from 0 to 6. And you should get that number. And when you write your volume out, you're going to take it out 3 places of accuracy. So it's going to be 1956.584. How dare you? 585. I think my mother was born that year.
He was born in
I was born in 97, okay? I'm young at heart, yeah. Second alpha and then trace. Second alpha trace. You're lying to me.
You trace alpha.
Second alpha. No, that's just, you guys are liars.
Oh, it did it for me.
That's fine. Are there any questions? Let's pause this again. We're going to do another one here. We got so much time left. Because I don't want you all to have too much free time, I know what you'll do with free time. Natick, I know what you'll do with all your free time.
Yo, I'm getting ready for a 420.
Okay? In our calculus book, we're going to do page 395. Shh. I want you to do numbers 1 to 15, just the odds. So you can check your answers. I want you to come in with questions. And, oh, that's not it. Come on now. Those are all areas. Those are area questions. They shouldn't be that difficult, okay? Page 407, I want you to do numbers. Let me see here. What's good? 23 to 357. Ha ha ha. The 31 odd. Ah, that's the happiest sigh I've ever heard. This is good. Okay. That's a 31, obviously.